Do you feel this reality in your bones, or do you understand this reality mathematically? You know it's right, you use it all the time, but still your mind can't fully wrap itself around it?
I'm pretty comfortable with it.
Hey everyone, thanks for joining us. Today our conversation will be in one of the areas of physics that I think is a real sweet spot of the kinds of conversations that we have. It's in the arena of quantum mechanics, quantum physics, but the focus will be more on the emerging arena of quantum computing, quantum information science. And I'm so pleased that we have one of the great leaders of the field who is joining us. That's John Preskill, who is the Richard P. Feynman Professor of Theoretical Physics at the California Institute of Technology, where he directs the Institute for Quantum Information and Matter. And he is joining us now from his office at Caltech. So welcome, John. Thanks for joining us.
Hi, Brian. Good to see you.
Good to see you, as always. You know, we're entering now the 100th anniversary of quantum mechanics. You know, you can date it to whatever, 1925 with Heisenberg, matrix mechanics, 1926, Schrödinger, 1927, you know, some of the confirmations with the effective version of double slit. So just to get us going, where would you say we are in quantum mechanics? Is it a done deal? Are there open issues that you think are vital to the next phase of understanding? How would you characterize it?
Well, I think we could characterize the first 100 years of quantum mechanics by saying that we got some useful insights into the features of systems of many particles that are weakly interacting with one another, like electrons and semiconductors and the behavior of photons. And that led to insights that were valuable, both scientifically and technologically, like allowing us to put millions of transistors on a chip and lasers and so on. What I think we're looking forward to now in the next 100 years is getting comparable insights into the behavior of many particles that are very profoundly entangled with one another. That's the word we use when the particles are so strongly correlated that their collective properties are very complex and hard to predict with the conventional computing technologies we have now. And that's really what quantum computing is starting to explore.
Yeah, very much so. So we're going to get there in a moment, but I want to just take a step back. I mean, many in our audience are familiar with the general ideas of quantum mechanics, but I always think there's value in just walking through the essence of this way of describing the world. And then once we have that, we can then turn to the application of these ideas to quantum computing. So if you, no doubt you've taught quantum mechanics many times. You know, when I teach it, I tend to just say at the outset that there are basically three main ideas in quantum mechanics that are startling. The world is governed by probabilities. The world allows for superpositions, where things can be this way and that way at the same time, and that the world allows for quantum entanglement, sort of the big three ideas. Are those, to your mind, the big three as well, or how would you describe the essence of quantum physics to someone who doesn't know the subject?
I think those are the big three. And what was implied by what you said was that randomness, unpredictability, is an essential feature of quantum mechanics. So when we speak of probability, we mean something different in the context of quantum mechanics than we do when we talk about probability in everyday life. Usually we talk about probability like the probability that it's going to rain tomorrow, in the sense that we're ignorant of some of the features of the system that we're trying to predict. Quantum mechanics is different because there is intrinsic randomness. Even if you have a complete description of a physical system, you can't predict what you're going to see when you observe the system. That's really something new in physics.
And it's kind of crazy, right? I mean, this is one of the issues, not the only one by any means, that Einstein had. You know, he, I think, went to his grave imagining that maybe the probabilities in quantum physics were like those in weather reports, and we just didn't know the deepest description of reality, and that one day when we did, we'd realize that those probabilities were just an emergent feature of not having the full description. I mean, is that an accurate description of his thinking?
I think so. A pivotal moment in quantum mechanics was when John Bell pointed out that we can really do experiments to demonstrate that the quantum randomness is intrinsic. And there are features of quantum mechanics, quantum entanglement, which Einstein found troubling, but which experiments show we just have to live with.
And so if we're Einstein here now, I mean, maybe it's even worth just stepping back. So 1935, it actually was Einstein himself, together with two colleagues, Podolsky and Rosen, who pointed out this quality of quantum entanglement that then John Bell ran with in the 1960s. But just give us a brief synopsis. What did Einstein write about in 1935 with this idea?
Well, Einstein, in that 1935 paper with Podolsky and Rosen, was considering two particles which could be very far apart from one another, such that if you look at the particle, say, which I have here in my lab at Caltech, and you can measure either its momentum or its position, and then you would know with certainty the momentum or position of another particle, which could be very far away in another galaxy. And this seemed very disturbing to Einstein because it suggested that the principle of locality, which was very foundational in relativity, both special relativity and general relativity, seemed to be violated, or at least the spirit of it didn't seem compatible with that feature of quantum entanglement, and that led him to propose that there was something missing from our description of the quantum world. And it's surprising, perhaps, that other physicists didn't think this was such a big deal. They were quite dismissive, many of them. I mean, it was Einstein, so they paid attention. There were a few who thought Einstein was making a very cogent argument. Schrödinger was one. But this idea of quantum entanglement really did not get much attention from physicists until decades later. And again, it was Bell, I think, who realized that there's something very deep about it.
And so why do you think that was? I mean, some people point to the personality of Niels Bohr as this sort of overwhelmingly convincing physicist who, you know, you could walk into his office with one way of thinking about things. If it disagreed with Bohr, the odds were when you left the office after a conversation with him, you would have come around to his perspective. So is like the shadow of Niels Bohr, and this is not, you know, any real criticism of him. He was a wonderful physicist, obviously one of the greats. But did kind of the shadow of Niels Bohr just, you know, color people's perspective for decades, even in the face of these cogent arguments that suggested something needed to be thought through more fully?
Maybe so. Bohr was pushing the idea he called complementarity. And so he argued on that basis that, and he was onto something really, when he said, you know, we can't think of the measurement of a position and the momentum of a particle as compatible observations. You have to do one or the other. And what troubled Einstein was the other particles seemed to know what to do, whether you measured the momentum or the position. And I think part of the reason, well, by the way, Bohr, although he did have this very compelling personality, he could be very hard to understand.
Yeah.
He wrote a response to the Einstein-Podolsky-Rosen paper, and it's not so easy to tell what he's getting at, whereas the Einstein et al. Paper is actually quite clear.
Yeah.
And Bohr would sometimes, he would take great pride in the care he would put into writing. And it would go through draft after draft after draft until it got to the point that no one could understand it anymore. And that seems to be what happened in that case. But I think, what really surprised people was that there was something here you could test experimentally, and it took decades to realize that.
Yeah. There's even a rumor, I don't know if it's true, I've never checked on it myself, I probably should, that in one of Bohr's responses for a very long time, the published version or the version that was being passed around had 2 pages interchanged. And for a very long time, nobody even realized that was actually the case. But yeah, the shocking thing was, as you're saying, that 1960s, Bell realized that, I think the view that some people had, like I think Pauli is credited with saying that the Einsteinian criticism of quantum mechanics, that maybe objects actually have definite features, even though quantum mechanics is only able to describe the probabilities that they have one feature or another, which was sort of the conclusion he drew in that 1935 paper. Pauli said that was sort of like asking for counting angels on the head of a pin, because how would you ever know that an electron has this or that spin before you looked at it? Well, you need to look at it to determine if it has that spin. So to him, this became just an abstract, perhaps interesting question, but with no experimental consequences. And then John Bell, by basically just doing a little generalization of the entanglement setup, found that there were experimental consequences. And I guess, what was it, the 2022 Nobel Prize was awarded at least in part for the folks who wound up testing those consequences, right? I think, if I've got my Nobel Prize years correct. Is that right?
Yeah, that was Clauser, Spey, and Zeilinger, who all did experiments to test whether Bell's inequality, as we call it, is violated in experiments. Bell derived a consequence of Einstein's point of view, that point of view being that it's really determined even before you look at a quantum object what the outcome of an experiment will be. In other words, that probability arises from ignorance, as it does in ordinary situations. And Bell showed that if that were true, there were experimental consequences which were not satisfied in experiments.
Right. And so here we have this theory then where, according to the best experiments that we can currently do, particles don't have definite features before measured. There are a range of possible outcomes in any experiment, and the best quantum mechanics can do is predict the probabilities of getting one or another outcome. We have this theory in which distant objects seem to somehow, in some quantum mechanical way, know about each other, even though they're far apart, where the measurement that you do over here in some sense affects the measurement that you do over there. So, we teach this to our students, we understand the mathematics behind it. The question that I'm often asked, and I'd like to get your take on it, is, do you feel this reality in your bones, or do you understand this reality mathematically? It's right, you use it all the time, but still your mind can't fully wrap itself around it.
I'm pretty comfortable with it because, like you said, we know how to describe it in a mathematically precise way. We shouldn't be so shocked that the quantum world is different from the world of ordinary experience. Of course, we would like to understand why that ordinary experience is the way it is. In other words, why we don't see these strange quantum phenomena in everyday life. And I think we do understand something about that. By the way, just for clarity, I want to come back to your comment that in some sense, the particle here in Pasadena knows about your particle in New York. That does not mean that I can send an instantaneous signal from Pasadena to New York. It means that the correlations between what you see in New York and what I see in Pasadena are different than the correlations among ordinary objects. Quantum correlations are different.
Yeah. And that's a vital fact which some people describe as sort of relativity surviving by the skin of its teeth, in the face of quantum entanglement. I mean, Einstein's dictum that nothing can travel faster than the speed of light, that nothing is meant to refer in some way that we understand fairly well, that no signal, no information, no direct influence of any kind can exceed the speed of light. And as you're pointing out, the two particles, say in Pasadena and New York, when you measure one and you get up, and the other one you get up in terms of its spins, that's an interesting correlation, but you can't know about that correlation until you compare them, and that's a slower than light comparison. So it's random results in Pasadena, random results in New York, and the information only emerges upon that comparison. So in some sense, the information is distributed across space in a way that we would never anticipate classically. Is that a way that you would describe it as well?
I think so. And what's important to appreciate is that those correlations are different than ordinary correlations, has deep consequences. Right. And we appreciate those especially if we consider systems of many particles which are entangled with one another. These quantum particles sort of speak a different language than the language we understand or our conventional computers understand. So if you try to translate all the correlations among, a few hundred particles, like a few hundred quantum bits, into ordinary language, describe it in terms of bits, it's completely infeasible to do so. It's just completely, it's way too complicated. It would take more bits than the number of atoms in the visible universe. So this very different language of the quantum world means that with quantum systems, we can do some things that couldn't occur if physics were classical. And quantum computing, which surpasses what we can do with conventional computers for some applications, is one of those things.
Yeah. So I'd love to turn to quantum computing in just a second, but I want to do one small footnote, if you will, before we get there. When assessing the state of quantum mechanics, there are some who've emphasized, and this happens to be my perspective as well, that there's this gaping hole called the quantum measurement problem. When you've got a system, we don't, at least mathematically, have a full handle on how it is that an observation or a measurement coaxes one definite outcome from the range of possibilities that the quantum mathematics describes. Do you consider this to be a big hole, or just a detail that we'll figure out, or perhaps one that we already have? Where do you come down on the quantum measurement issue?
Well, it does seem worth noting that physicists disagree about these things, that there isn't really a broad consensus about the right way to think about what happens when a measurement is made on a quantum system. I do have my own preferred way of looking at it, which I share with other physicists, but not all, which is what we sometimes call the Everett interpretation, which basically says that measurement isn't something special or different. It means that some correlation gets established between the observer and the system that we're looking at. And I like that point of view because in some sense, but in another sense not, it's the simplest point of view, that there's a law of how systems change when they interact according to quantum mechanics, and that's enough to understand what happens when a measurement is made. But this is a controversial opinion.
And so, I mean, you're right. Obviously, from the mathematical standpoint, the beauty of Everett's proposal, often called the many worlds interpretation, is that it's just the equation that Erwin Schrödinger wrote down in 1926. It just continues to evolve the system forward in time. And it's up to us to recognize that there are certain configurations of the state of the system that we human beings would describe as a world, a reality that we inhabit.
There's a price we pay for that, which is we have to include the observer in the quantum description to understand why when I make an observation, I see a definite outcome. It means a correlation is established between the system and my apparatus or my brain. I'm willing to pay that price. I think it makes perfect sense that if we're going to describe ourselves interacting with the quantum world, then we should be subject to the quantum description ourselves.
Right.
But this would not have been Bohr's opinion, I don't think. Well, shouldn't put words in his mouth, but he thought there really was a kind of cut between the classical world and the quantum world, and information in some sense gets across that cut when a measurement occurs.
Yeah, no, I think you're absolutely right on your view of what Bohr would have said, because I think the historical record shows that John Wheeler, who was Everett's supervisor at Princeton, had Everett go to Copenhagen to discuss these ideas with Bohr. And I don't know the exact historical record, but Bohr dismissed pretty definitively that this was the way of thinking about things. Because you're right, and his view was you got small things where quantum mechanics works, big things like us where you don't use that language at all. So including the observer in the quantum formalism would seem to be the direct opposite, anathema to Bohr's version, or vision, I should say, of how quantum mechanics works.
John Wheeler was very interesting. I actually took a class from him when I was an undergraduate at Princeton. And it was a full-year class which kind of covered everything in physics. And as you can imagine, if you know about Wheeler, it was very idiosyncratic, the way he would describe things. But for me, very inspiring.
Yeah, no, I really only met Wheeler once. When I was writing my first book, The Elegant Universe, I went out to talk to Wheeler about various ideas of gravity and so forth, and we went to lunch, and it was one of those memorable moments just for me as not just a physicist, but as a human being, to sit across from someone who just was so immersed, enamored with these big ideas, and just loved talking about these things, and certainly had an unusual way of describing things and thinking about things. But before we move on from many worlds and turn to quantum computing, you mentioned there was one price to pay, which we mentioned is including the observer in the formalism of quantum physics. Some would also say there's another price that you pay, although, as you say, it's controversial. There are some physicists who think that the price I'm about to mention has been paid in full, and it's not an issue whatsoever, which is, in quantum mechanics, you can only predict probabilities, and we have an intuition about probabilities. Low probability means less likely, high probability means more likely. But kind of the weird thing in the many worlds approach is, since every outcome happens in some universe, even the lowest probabilistic possibility, you are assured that it is realized. And some would say, in what sense then is it unlikely? In what sense does probability actually work if every outcome happens? And people have stood on their head to make sense of this using decision theoretic arguments. Oxford School has a whole approach to this. Does this issue have a pull on you?
It does. I think one can go pretty far in understanding the origin of probabilities by, first of all, recognizing that what we call decoherence is a big part of the story, which is important for being able to speak about measurements having outcomes, that having unambiguous correlations between what is observed and the observer. But then in addition, there are symmetry arguments you can use to say that, outcomes that occur in the wave function with the same amplitude should be assigned equal probabilities. And that can take you pretty far in understanding what we call the Born rule, how probabilities are assigned to outcomes.
And so do you think it's a done deal, or there are people who I've spoken with over the years, who've worked on this, who seem to have gotten to a place where they're so exhausted in talking about it that they say it's done, it's finished. They don't want to even talk about it anymore. And, frankly, even today I was just clicking around online, and I saw a video. I didn't look at it yet, but it was, David Deutsch And the title of the video was, "There's Only One Interpretation of Quantum Mechanics." And I know which one that video must be espousing. It has to be the many worlds approach, because his view is it's done, it's finished, this is the right approach. I'm not convinced of that. And I've spent some time thinking about this, the mathematical side of things. I've been yelled at by philosophers, who are not convinced of this. Have you interrogated this to the point where you feel it is correct at the level that, say, David Deutsch is committed to it, or are you not quite there yet?
Well, I don't really agree with the statement that you attributed to David Deutsch, which he's been saying this for decades. I guess I'd make 2 points. First of all, these questions about foundations only deeply interest me to the extent that they can be translated into things that are experimentally testable. So if different people have different ways in which they want to describe the quantum formalism, but they agree on the outcome of all proposed experiments, then I don't really care very much. But like I said, I like the Everett point of view because of its simplicity, as you put it. Nothing's happening but the Schrödinger equation. And the question I ask myself is, suppose that we're correct. Would the world seem any different than what we observe and experience? And I don't see a way in which it would be any different. So to that extent, I feel satisfied.
So one more question, because I don't want to belabor this point, but it's one that grabs me. So just one more question. So when you think about the role of physics, like part of, for me, the role of physics is that I can tell a like compelling narrative about what's actually happening in the world, what's real, the dynamics that controls what's real. To me, it doesn't feel enough to be able to just have predictions confirmed by experiment. I want physics to lift the curtain and show me the behind the scenes drama. And so if one does take a many worlds point of view in thinking about quantum mechanics, does that mean that the behind the scenes drama is, if you don't mind me just using the technical language for a moment, is the world a universal wave function governed by the Schrödinger equation living in some Hilbert space and it's just dynamically evolving forward with the Schrödinger equation? Is that the true reality that we inhabit?
Of course, I can't give a definitive answer to this question. I don't think anyone can. But I am comfortable with that being the true reality. And of course, I agree with you that our goal in physics is not just to be able to predict outcomes of experiments, but to, whatever this means, understand how nature works. And I think, of course, I'm not saying we understand everything about quantum mechanics. I don't really think that. But I think this is a picture which I feel is consistent and which one can understand. And until we have experimental evidence to dissuade me, I'm comfortable with provisionally accepting this is the way nature really works.
Yeah, absolutely. All right, so then moving to quantum computing or quantum information science, I think the segue from the many worlds interpretation perhaps is a fine way in. I don't work on quantum computing at all, but nevertheless I'm often asked about it. I mean, I think I understand the basics of the subject, often in a very hand-wavy manner. If someone is pressing me on how is it that quantum computing could do better than classical computing, there are many ways of approaching that question, and I'd love to explore them with you. But one way is, if you take the many worlds interpretation, as many people have noted, it's as if you're using computations in all of those universes in parallel to get to the answer that you're searching for. And clearly, in a one universe theory, like the classical universe of Isaac Newton, you wouldn't have as much power compared to a many universe version of quantum mechanics in which these calculations can happen in parallel. Is that a way that you find useful to think about the power of quantum computing?
Well, this raises a good point about interpretations, why they're useful, why we care about them, I think different interpretations of the quantum reality give you different intuition about things. So I think for David Deutsch, looking at quantum computation from the perspective of the Everett view of the world was helpful for him in proposing that quantum computers would be powerful compared to conventional computers. On the other hand, you don't have to believe in the Everett interpretation to agree with rigorous statements we can make that as long as quantum mechanics is correct, we can solve certain problems with enormous speed-ups using quantum computers compared to conventional computers. So if that interpretation makes you happy about the origin of the power of a quantum computer, I don't want to deny you that happiness.
Thank you. So how then would you, maybe without invoking the many worlds interpretation, what would be a more down-to-earth, say, version of how quantum computing leverages the way that information is encoded in a quantum system to be able to do information processing that you couldn't do in a classical system?
Well, we touched on this earlier. I think it has to do with the extreme complexity of describing many entangled quantum bits, many entangled particles in terms of classical language. And because quantum entanglement really is different from classical probability, we think that if you have many entangled qubits, there is no succinct description which we can write down or store in the memory of a conventional computer of all the correlations among the particles. And so if we consider processing the qubits, in general, that's not something we can emulate with a conventional computer. So that at least opens the possibility that quantum computers can do things that we could not hope to do with conventional computers that process bits.
And can we nail down on that, drill down that a little bit further? So, again, words that many in our audience are familiar with, perhaps it's just worth covering it. So when you talk about a qubit versus a classical bit, maybe just give us a sense of that first.
Right. So I think everybody understands the idea of a classical bit, which can be either a 0 or a 1, or can be in a computer encoded by a switch, which is either open or shut. And in computers, we have many bits, and we perform operations on them, and that's how we process information and do computations. Qubits have this property we spoke of earlier, that when you observe a qubit, even if you have a complete description of the state of that qubit, you can't necessarily predict the outcome. So one way of characterizing what's different about qubits from ordinary bits is that there are different ways to observe them, different ways to measure them, which are not compatible with one another. So, if you know that the outcome of, so to be a little bit more visual about it, one example of a qubit is the spin of a particle like an electron. And you can think of that as a little magnet which has an orientation in space. That's a little bit too literal. But if you know that when you observe it along the vertical direction, it's always going to be spin up, that's of no use to you when what you would like to know is what happens when you observe the spin along the horizontal direction, where you just get a random outcome. So that's an essential difference between bits and qubits. It's not clear why it would be useful, and maybe by itself it's not so useful for computation. That's where entanglement comes in, where I think, again, the key feature, the way I think about the power of quantum computing, is that it's just too hard to describe, in terms of ordinary bits, the state of many qubits.
And so just to give a feel for that, if we use the example of the spin of a particle, say, this is a 1 and that's a 0, the spin of an electron up or down. If you have two of these guys, classically, They could be like this, or that, or whatever orientation of my thumbs I may have missed in my little visual demonstration. But the entangled state that you're describing would not just be one of those four possibilities, but actually a combination of all of them at once. And as you increase the number of spins, you have an exponential increase in the number of combinations that can all contribute to the description of the overall collection of n qubits. And so I gather it's that exponential increase in the number of potential correlations between the spins of these n particles that you're describing when you're saying it's just too hard in a classical description to describe all of those.
Well, that's essentially right, but there's a nuance, which is if you have 100 bits, there are a vast number of possible configurations for 100 bits too. It's 2 to the 100th power. It's a huge number. The difference is that for any one of those, it's very simple to describe. You just write down 100 bits. You can put that on a piece of paper. Where quantum is different is that even if you have, the most complete description of those 100 qubits, quantum bits, that nature will allow us to have, there isn't any way of writing it down in terms of ordinary bits. The word we use is superposition. It sort of all those different 2 to the 100 bit strings are represented in the state, and you would have to know how to weight them all to write down the quantum state. And that's
so
just
there aren't even enough particles in the observable universe to account for the number of terms in that superposition, number of terms required to describe the state of this 100 qubit system.
Well, 100 isn't quite enough. I'd need about 300. For about 300.
Yeah. So with about 10 to the 90 particles or something like that, that's 2
right.
to whatever power. Yes, exactly.
Right.
So presumably then part of the power of quantum computing is, computation is information processing. It's going from one configuration, processing the information in that to a distinct configuration. If you're doing an operation on this superposition that has 2 to the 100 terms or 2 to the 300 terms or whatever the number of qubits you happen to have, you're doing an operation that is influencing all of the terms. And so it's this enormous information processing that takes place when you are acting on a quantum state compared to the information processing that would take place on any term individually, which is all that a classical system would have access to. Is that, again, a way of giving a feel for the exponential quality of information processing in a quantum setting?
Yeah, I think that's pretty good. Maybe we should emphasize an important point, though, which is that if we're interested in what is computable, if we don't care how long it takes, then quantum computing doesn't change that. Some think, there's this beautiful theory of computability that goes back to Turing and others. There are some things that are just not computable no matter how much time you have. And for quantum computing, what is computable is the same as for conventional computing. The difference is efficiency. So some of those ways of manipulating 100 qubits are just too hard for a conventional computer to do in a reasonable amount of time. If you gave it much longer than the age of the universe, the quantum computer would be able, or the classical computer would be able to imitate what the quantum computer does. I mean, if our viewers know what a matrix is, the quantum computation is, you could describe it in principle by this huge matrix, which, acts on 2 to the 100 numbers or some very large number. But that matrix sort of encodes what the quantum computation is doing, but it's vastly complex to describe in classical language.
Right. And that obviously from a practical standpoint can make all the difference in the world, since we finite lifetime beings are interested in computations that we can get through in a reasonable period of time. And the exponential qualities of the quantum version can make something that classically would take, much, much longer, something that we can actually, in a feasible period of time, accomplish. And I'd love to get a sense of how we do that and where we are in that particular subject. And so just as sort of a lead into that, just from a personal standpoint, you began your professional career, I gather, doing particle physics and cosmology, back in the 80s and maybe even into the 90s. You then made a shift to the kind of quantum information science that we're talking about here. What is it that drew you to make that transition?
Yeah, I get this question a lot. And I'm not exactly sure how to answer it, but I, like you, when I was a student, was attracted to fundamental particle physics because I thought these are the deepest questions about how nature works. And it's just so exciting to understand the structure of matter at these very small distance scales. When I was a student in the 1970s, it was a very exciting time in particle physics. We were just acquiring a confirmation of the so-called standard model of particle physics, or core theory, that describes very precisely, as experiments have confirmed, most of the interactions that we know of in nature, with gravitation being an exception. I came along a little bit too late to participate in discovering the standard model. For me and my generation, we were excited about physics beyond the standard model. What explained why the standard model is the way it is, and for that we were going to need data. And we were waiting for the next powerful accelerator that was going to give us that data. In the early 90s, the superconducting super collider was under construction in Texas, and we thought that was going to help us answer these questions about physics beyond the standard model. So it was quite a blow to particle physics when that project was canceled in 1993. And that caused me and others to do some soul searching about what scientific direction to pursue. Now, in the meantime, while I was waiting for the SSC to turn on, I got interested in other more abstruse topics, like how do you describe a black hole quantum mechanically? Stephen Hawking had made this amazing observation that because of quantum entanglement, black holes emit radiation. That meant black holes had enormous entropy. We wanted to understand how to interpret that, and I was thinking about things like that. And that led me to acquire some knowledge of the then very new field of quantum information, where interesting things were happening in the early 1990s, like the idea of quantum teleportation was discovered, and people were thinking about how quantum mechanics allows encryption, which is invulnerable to eavesdropping. So I was learning about those things out of intellectual interest, but also because I thought it might help me understand black holes better. And then Peter Shor in 1994 discovered that there are some problems for which we think it takes an unreasonable amount of time to solve them with conventional computers, but quantum computers could solve them fast. An example is the problem of finding prime factors of large composite numbers. And although I didn't have a background in algorithms or computational complexity, I was immediately fascinated by this idea. I thought, this is amazing. The difference between a hard problem that is just too hard to solve, no matter how advanced our technology, versus an easy problem, which we can solve with computers, well, it makes a difference whether it's a quantum world or a classical one, and it is a quantum world. So the difference between hard and easy is the way it is because we live in a quantum world. And I just wanted to understand that idea better. So first, without really intending it to be a shift in my career direction, just out of curiosity, I tried to learn more about quantum computing. It was a smaller field then, so one could kind of acquire familiarity with most of the things that were going on pretty quickly. It also helped me to teach a class. As you know, that's the best way to learn something. And then I kept finding interesting things to think about. But I'll tell you, from the start, I was not... obviously, it's exciting to think about quantum computers that can have an impact on society because we can solve problems that would otherwise be too hard to solve. But I was interested from the beginning in quantum information as a way of looking at how nature works. And I think as we've understood quantum computing better, it has given us insight into fundamental physics as well.
So it's a fascinating personal story and journey as a physicist, but another reason why I bring this up is because I think it's pretty vital for people to recognize that it's not enough to have a formalism in which information can be processed in a fundamentally quantum mechanical way in the manner that we were describing, having a superposition of many possibilities that are all being updated in parallel in the way that we describe. If you don't have an algorithm that can leverage that particular way of doing computation to extract the answer of interest, there's nothing you can do with it. I mean, another way of saying it, going back to the many worlds approach, is if you're doing all these calculations in parallel in all these different universes, then you're getting every possible outcome. How do you somehow select the one outcome from the many that's of interest to you? And in some sense, that's what Peter Shor gave an algorithm for in this problem of prime factorization. So what, in your mind, what is the role of finding algorithms that, problem by problem can actually be applied to use this quantum computational capacity?
Right. So there's an art to finding quantum algorithms that actually are useful in the sense that they do things that are hard to do with conventional computers. One way of thinking about the power, a little bit different than what we said before, though related, is, as you said, quantum mechanics is all about probabilities. But in quantum mechanics, we can think of probabilities as being related to what we call amplitudes. And we assign amplitudes to different configurations. And the thing about amplitudes is they're not necessarily positive. Probabilities can't be, you can't say there's a probability of minus 50% it's going to rain tomorrow. Probabilities are always non-negative. Amplitudes can be positive and negative. And so what a quantum computer does, and if you like, you can think of this from kind of the Everett point of view, is it does lots of computations all in parallel because it's acting on some superposition of bit strength. That's not enough, though, for the computation to be useful. What we want to happen is when we assign amplitudes to all the paths that the quantum computer can take from the input to the output, that we want all the wrong answers to cancel out. And that's actually possible with amplitudes. With probabilities, they only add up to give bigger numbers. But with amplitudes, the positive ones can cancel the negative ones. And so the way quantum algorithms work, when they work, is the answers we don't want cancel out, and we're left with just the answers that are useful. And there are only certain problems which have the right structure for us to have understood how to get that big quantum advantage.
And so, when I first went through Peter Shor's algorithm, it's so brilliant the way properties of number theory, something that doesn't feel like it's physics, it's just a property of abstract properties of numbers, can be used to get those cancellations that you're talking about, and having the constructive interference as the positive numbers coming together only on the terms that give the factorization of the composite number. So it's utterly brilliant, but then when you look at it, at least for someone from the outside like myself, it feels so specific to that very particular problem. So can you give me an intuition or a sense, how likely is it, given a particular problem, that there is some quantum mechanically relevant algorithm that would be useful to solve that problem?
Well, one thing we can say is there are lots of problems for which we don't expect spectacular speed-ups from quantum computation, like in the problem that Shor considered. We often speak of problems that are in NP. What it means is that once you get the answer, you can check it. But within that class of problems for which the answer can be checked, there are problems which are the hardest type within that class. They're called NP complete or NP hard. And these are very familiar problems which are broadly useful. Optimization problems. You're trying to do scheduling. The traveling salesman problem is a famous example where you're trying to find the shortest route that visits a list of cities. Some problems in portfolio optimization and so on. These are all NP hard problems. So what do we know about that? Well, why are they so hard? Roughly speaking, it's because there isn't a much better way to solve those problems than just exhaustively searching for the right answer among all possible answers, like all possible routes that visit the cities. What's the shortest one? So that's really hard because there are a huge number of possibilities you have to check. Now, we do know that quantum computers can speed up that kind of exhaustive search for the answer. However, it's not nearly as spectacular a speed up as in Shor's algorithm. It's what we call a quadratic speed up. That means the time, the number of steps that you need on the quantum computer to search among all possible candidate solutions goes like the square root of the time it would take on a conventional computer. Now that's interesting, and maybe in the long run it'll be useful. But the really exciting applications of quantum computing are the ones for which we have really spectacular speed-ups, exponential speed-ups. And that's where we can, imagine, say, with Shor's algorithm, factoring a number in a couple of hours with a future quantum computer that would take much longer than the age of the universe to solve with a conventional computer. And the truth is, problems that have the right structure for that to be possible are special. And part of the art of understanding the applications of quantum computation is understanding what problems allow that. But there's a really important class of such problems. Since we were talking about 100 years of quantum mechanics, already back in the 20s, not more than a year or two after the Schrödinger equation was proposed, Paul Dirac, a great theoretical physicist who made many pioneering contributions to quantum physics, made the following point. He said, well, now we really have a complete theory of everything that matters in everyday life. It's just the theory of electrons interacting with one another electromagnetically and interacting with atomic nuclei. It's described by the Schrödinger equation, and that underlies all of chemistry and all of materials and everything that's built on those sciences. The only trouble being that it's just too hard to solve the equations. We know exactly what the equations are, but it's too hard. And in the Dirac's case, back then computation wasn't something you did with a machine, it was something you did with a pencil and paper, and he was thinking about just a handful of electrons. Now, Richard Feynman's scientific hero was Paul Dirac. Somehow it took 50 years for somebody to say, and it was Feynman in the early 1980s, well, if you want a machine that can solve problems having to do with the quantum behavior of many electrons, it should be a quantum machine, not a conventional machine. And of the applications we currently foresee for quantum computing, those are the ones that have the greatest potential to positively impact society, the applications to chemistry and materials. Now, a lot of computational power is used to solve such problems, to understand complex molecules and novel materials, but there are limitations on how far you can go because those systems can have a lot of entanglement quantum computers will go farther, and I think we can be optimistic that that will turn out to be broadly useful eventually.
Right. Now, en route to that, if we could just turn to the relevant subject of the challenges to actually, in practice, doing these quantum computations, there are a number of hurdles, but maybe we could start with the word that you mentioned briefly before, this notion of decoherence, this idea that at the heart of quantum computation is that you have these entangled qubits, so that exponentially large number of correlations between their various possible states are all included in the state of the system, whereas environmental influence kind of acts like a measurer and causes those qubits to lose that quantum entanglement quality. It's as if you're measuring the qubits and forcing them to be either up or down, as opposed to that mixture that allows for this exponential number of correlations. So is that perhaps one of the key issues in trying to put this into practice, this need to isolate the system from environmental influence that will ruin the coherence of the entangled state?
It is indeed one of the key issues. We brought up decoherence earlier in our conversation in the context of, well, if this is a quantum world, why does everyday experience seem to be classical, well described by classical physics? It's because of this phenomenon of decoherence. So what is it? You see, it stems from a fundamental distinction between ordinary classical information and quantum information, namely that you can't observe a quantum system without disturbing it in some uncontrollable way. Whereas it's, one can look at a bit string without changing it. You can't do that with a quantum state. And even if we don't observe the quantum system ourselves, if information about it leaks to the outside world where it could, in principle, be observed, that's just as bad. So as you put very aptly, if we want to run a quantum computation and get the right answer, and we don't want it to behave like a classical computer because of decoherence, we need to keep the information that's being processed nearly perfectly isolated from the outside world. And that's really hard. So after all, it was over 40 years ago that Feynman suggested we should build quantum computers to solve many particle problems in quantum physics. And we're just getting to the point in the last few years where quantum computers are capable of doing interesting things. So evidently it's hard. And one of the hardest things is fighting off the destructive effects of decoherence.
And so over the course of, say, the last 30 years or 25, 30 years that you've been primarily thinking about quantum computing, did it matter to you that it seemed that having an actual workable quantum computational system that would be somehow sufficiently isolated or with sufficient quantum error correction, something I'd like to talk about in just a moment, so I don't mean to jump the gun, but were there times where you felt like, what am I doing? This is never going to be realized, or did it not matter because it was the interesting theoretical problems and they had you captivated and you didn't care about actually realizing it physically?
Well, it would have been much less interesting to me if I didn't think we'd ever be able to do it in practice. But it is a compelling theoretical question. And I think quantum error correction, which we'll come to in a moment, is a real fundamental advance in our understanding of physics. Because what it says is, despite the pervasive effects of decoherence, which normally make very large, complex systems behave classically, so that their quantum effects are disguised, we've learned in principle how to make a very complex quantum system retain its quantum character and behave in a profoundly quantum mechanical way. So, decades ago, when one spoke of quantum physics, it was implicit one was talking about really small things, like individual atoms or electrons. And now we appreciate that something that's very large and complex can behave in a way where quantum mechanics is essential for describing what it does. And I think that's a fundamental insight.
Yeah. So sort of there's two sides to this coin. I mean, just so people can draw a connection to something they're more familiar with, Schrodinger's cat is this famous example of a macroscopic system that Schrodinger cleverly designed a situation where that cat would be in a superposition of two states that are obviously different, cat dead, cat alive. And the question was, why don't we ever see things like that? We pretty much have an answer to that now from the decoherence that you're talking about. The environment, even the molecules within the cat itself, they all act to measure the state of the particles making up the cat, ensuring that it will either be dead or alive. They will destroy the coherence of the superposed state of dead and alive, making it one or the other, a very classical description. Our goal, though, in quantum computation is to keep that cat, if you will, in that mixed state of both dead and alive. And there are techniques for doing that that you make reference to. And this takes us to this whole arena of quantum error correction. So what is that and how does it work in practice?
Well, of course, you do it with entanglement. So what do I mean by that? Let's circle back to what quantum entanglement is all about. So suppose you consider a system with many parts, many atoms. For purposes of visualization, suppose it's a book, and it consists of 100 pages. Okay, now if it's an ordinary book, it's written in bits, you can read the pages one at a time, and after you've read all the pages, you've acquired all the information that's in the book, and you know everything that the book says. Quantum systems aren't like that. If it's a quantum book, it's written in qubits where the pages are entangled with one another. What does it mean? It means if you look at a single page, you just see random gibberish. You can look at all 100 pages one at a time. And when you're done looking at all the pages, you still know almost nothing about what's in the book. And the reason is, in the quantum book, in this highly entangled system, the information that's stored in the book, and there's lots of information there, it's not on the individual pages. It's almost entirely in the correlations among the pages. That's how quantum entanglement works. And at a high level, the idea of quantum error correction is, I want to avoid decoherence. I don't want information about what's in my quantum memory to leak to the outside. Well, the environment keeps interacting with the system, kicking it around. But it does that locally. It doesn't make a collective observation on 100 pages at once or 50 pages at once. It's kind of kicking a single page each time. And there's no information on the single page. So the environment isn't acquiring information about what's stored in that quantum memory when it interacts with it locally. So the idea of quantum error correction, if we want to protect information from damage, from decoherence, we should store it in this very highly entangled way among many qubits, many particles. And furthermore, we've understood how to efficiently process information that's encoded in that very highly entangled way. That's what we call quantum error correcting codes and fault-tolerant quantum computation, and that's how we think the powerful quantum computers, which we hope to have in a few decades, are going to work.
And so I gather in practice the way this works is you have a single qubit that abstractly would be one of the qubits in your quantum computer. Behind the scenes, you want to have many physical qubits that encode the information in that single, I gather the language is logical qubit. They want to encode the information in that logical qubit across this collection of physical qubits entangled in such a way that if some errant photon from the environment hits one of these physical qubits and knocks it around or something, you don't destroy the overall information that's stored in the correlations across them. Is that the way this is done, more or less, in practice?
Yeah, that was a good description. I can't really improve on what you said. The information is stored in a very redundant way, but and that's why we get protection. Of course, there's a notion of error correction in the classical world as well when we're communicating, as I guess we are now, over some wireless connection, or if we're using cell phones. Those messages get garbled a little bit, and the way we make the information reliable is by using some redundant encoding so that you can knock out some of the bits, but the information can still be recovered. And quantum error correction works according to that same principle, that with a redundant encoding, we can protect the information. But there's this additional subtlety, which is the information has to be inaccessible locally if you look at just a few qubits at a time.
And I guess part of the other challenge, if one is just thinking about this classically you can make many Xerox copies of a piece of information. Quantum mechanically, there's a challenge to doing that. Maybe it's worth spending a moment on that.
Yeah, that's one of the interesting ways in which quantum information is different from ordinary information. We can't make perfect copies of unknown quantum states. It's easy to make a machine in the classical world which will receive a classical bit string and can make another copy of it or make 1,000 copies of it. But quantum physics doesn't allow that. It has to do with this feature we talked about earlier, that there are different complementary ways of looking at a qubit. And if you look at it in the right way, if it's been prepared as a spin-up electron or spin down, and you observe whether it's spin up or spin down, then you know exactly the state of the qubit and you can copy it. But if you look at it in the wrong way, like you ask, is it pointing to the left or the right on a horizontal axis, then you're going to damage the information. So if you don't know what way to look at the qubit, you can't make a perfect copy of it. And that's called the no cloning theorem. And at first, it made people a little pessimistic about whether quantum error correction could really work. But that obstacle was overcome. So we understand theoretically now that with enough redundancy, we can make a quantum computer extremely reliable if it's accurate enough to begin with. So, in a quantum computation, we're performing operations on pairs of qubits, and those are imperfect. But as long as they're not extremely noisy, then quantum error correction will work, and those logical protected qubits will have very low error rates. We're going to have to scale things up a lot because by some estimates, we would like to have an error rate at that logical level on the protected qubits, which is 1 in a billion, 1 in a trillion. And we're nowhere near that now with the physical qubits. It's about 1 in 1,000 under the best conditions. So we've got to cross that enormous chasm of, say, 9 orders of magnitude in error rate. Quantum error correction is the only possible way we can foresee of doing that, but it means we'll need a lot more physical qubits. And so that's one of the big challenges now, is scaling up quantum computers to the point where quantum error correction can really be used in a productive way.
And so just those numbers are interesting to hear. So state of the art, if one is looking at the error rate of a quantum operation, maybe a single operation on a pair of qubits, what is the best error rate that people can achieve today?
It's about 1 in 1,000.
1 in 1,000.
And that's been done. There are a lot of different modalities. We can get into that if you like as well. But I think the best error rates are quantum computers that are based on trapped ions, on trapping electrically charged atoms with electromagnetic fields, and error rates at the 1 in 1,000 level are achievable even in devices that have multiple qubits. Another one of the top technological contenders uses electrical circuits at very low temperature, superconducting circuits, and there the error rates in multi-qubit devices are not quite that good, but they're a factor of 2 or 3 worse.
And then have they implemented quantum error correction in those systems? And if so, how many redundant qubits do they have for a given logical qubit at the state of play today?
Well, the state of the art is reflected pretty well in a demonstration that was done by the Google Quantum AI team last year. And what they did in a device which has an error rate, which is a few times 10 to the minus 3 at the physical level, is they constructed quantum error correcting codes where a single logical qubit was encoded in either 9 or 25 or 49 physical qubits, and the objective was to see that the error rate for that protected qubit improved as you went up to a larger code. And they showed that the error rate improves by about a factor of 2 when you go from 9 to 25 and 25 to 49, each time about a factor of 2 in the number of physical qubits. So that indicates that if you could continue to scale, you could make the error rates much smaller. Of course, we would like those physical error rates to improve as well, and then you'll be able to get an improvement by more than a factor of 2 as you scale up the code. And error correction demonstrations have also been done in some of the other modalities, both ion traps and neutral atoms, which are trapped by laser tweezers. So it's an exciting time right now.
And so just to, again, give people a sense, so when you refer to trapped ions or superconducting circuits, these are all technological ways of realizing the abstract idea of having a qubit being, an atom in its ground state, or I guess an excited state, that sort of the 0 and 1, and then the mixture between them would be the qubit, and similar ideas for the other modalities, the other technologies you made reference to?
That's correct. So in the case of an ion trap, for example, well, of course, no matter what the hardware modality is, the qubit has to be physically instantiated somehow, encoded in some physical system. And it could be a single atom. This is, by the way, a rather remarkable thing. If you look at it from the perspective of where the technology was a few decades ago, we can routinely manipulate individual atoms, and that's how some of these quantum computing modalities work. In the case of an ion trap, each qubit is carried by a single atom, which can either be in its lowest energy state or some higher energy state, where that higher energy state takes a long time to decay back to the lower energy state. That can make a good qubit. And as with all the modalities, the tricky thing is getting 2 qubits to talk to one another to do those operations on pairs of qubits. And there's a way of doing that in an ion trap that takes advantage of the fact that the ions vibrate in the trap because of their electromagnetic repulsion. In the case of these superconducting circuits, you can think of that as kind of like an artificial atom, which also can be in either its lowest energy state or an excited state. In that case, these artificial atoms have to be very carefully fabricated, and you have to make them out of good materials, and that's currently a limitation. Unlike atoms, which are good qubits, kind of intrinsically. But there are some advantages to the superconducting circuits. For one thing, you can do much faster operations, and that's going to matter in the long run because, as we were discussing earlier, we're not very patient, and we want to get the answer to a computation as quickly as we can.
But it's an interesting spectrum where you have individual electrons or atoms on the one hand being the instantiation of the qubit, but with a superconducting circuit, it's like billions of electrons in some sense being the substrate in which this singular artificial atom can be in a mixture of 2 potential quantum states.
Yeah, that's right. I would say both technologies are quite remarkable in different ways. As I said a moment ago, it's kind of amazing that we can manipulate with high precision a single atom. In the case of the superconducting circuits, the qubit is encoded in the collective motion of billions of pairs of electrons, but we've learned how to make that behave as though it were a single atom.
It's pretty amazing. And so, naturally with a lot of news reports that happen periodically regarding the various companies out there, you made reference to Google, Amazon, others as well, Continuum and so forth. At times, there are reports that quantum computation has reached, I guess, the term that you may have coined, quantum supremacy, doing something that a classical computer could not do. Sometimes people claim that these reports are hyped. How should we think, where do we stand on this idea of quantum supremacy?
Well, there's no question there's a lot of hype, but so I suggested the term quantum supremacy about 15 years ago. And what I was trying to get, and the word was new, but not the idea, of course, what I was trying to emphasize was that it's really kind of a pivotal time in the history of technology on Earth. We're getting to the point where we can control quantum systems well enough to make them do things that are too hard to do with conventional computers. And that's kind of a milestone in physics. And I was trying to emphasize that to the extent that we can, we should try to validate in experiments that's really the case. It's like testing quantum mechanics in a regime that we never had access to before. So I think from a fundamental physics point of view, that's important. But really, what people call quantum supremacy typically today is just a kind of benchmark for a quantum computer. It doesn't mean that it's doing something useful that people care about. The goal was just to have the quantum computer perform some task which one could cogently argue would be too hard to do with a conventional computer, and that task was not of any particular practical interest other than for the purpose of benchmarking the quantum computer. So I think by using the word supremacy, I may have amplified the hype a little bit, because it sounds like the quantum computer is now ready to take over the world. Well, that isn't really what was intended. It was just that we've gotten to the point where the quantum systems are sufficiently complex that they can do something that's hard to do with conventional technology.
And so the obvious next question, of course, is where do you see the timeline when the quantum computation will do something not only that, in some artificial problem is more than a classical computer can do, but that we will routinely turn to them, as our mode of trying to resolve things that we care about?
Well, the first thing I would say is that the quantum technology that we have now is already interesting from the point of view of scientific exploration. I think we can study the behavior of many particles strongly interacting quantum mechanically in ways that we couldn't before, and we can expect surprises, as we always expect when we do experiments in a regime that we haven't had access to before. And to some extent, that's already happening. If you study the dynamics of hundreds of qubits in some of these platforms, some unexpected things are seen, and then that's causes some good back and forth between theory and experiment. The theorists try to explain it, further simulations or computations are done, and that's all great. But I think your question is probably more about broader societal impact or economic impact. We have all these companies, hundreds of them actually, who are trying to develop quantum computing hardware or software or control systems or finding new applications, and in the end they'd like to make money. There it's hard to say how far broad impact lies, but I think error correction is going to very likely be essential for running applications that people care about. I also think that it's going to be kind of a hybrid of classical and quantum computing that will be used for applications where conventional computing alone doesn't suffice. So I'd be surprised if this happened in 10 years. I think other people are more optimistic, and of course, with substantial investment and breakthroughs, maybe it can happen faster. And of course, I hope it does. 20 years, I think, is realistic. I think between 10 and 20 years is a reasonable estimate. But the truth is, nobody really knows, because we've got some big problems to solve.
I mean, do you think that AI is going to be an integral part of that progress? And moreover, do you think progress in quantum computing is going to augment AI? Is there sort of an interesting conversation between these two areas that's going to drive things forward?
Yeah, there are many interesting aspects to this question, which is a very natural one to ask. For example, I emphasize the potential of quantum computing to enlighten us concerning problems in chemistry and material science. Well, people are using AI for that as well. And I said that, Dirac said that these problems are too hard to solve with conventional computers, but that's not completely fair, because we do have lots of heuristic classical algorithms that people use routinely and successfully to solve problems in chemistry and material science. So with quantum computing, we're targeting a relatively small corner of many particle quantum mechanics where those classical methods break down. And there, AI still is not empowered to be very helpful, because we don't have the training data in that highly correlated, regime of many particles to generalize, to make predictions about new situations. But as quantum computing advances, I think conventional AI, meaning run on classical computers, and quantum computing are going to work together. With quantum computing, we'll be able to do new kinds of experiments and get data that conventional AI will then be able to generalize from. Now, It's also natural to wonder, can quantum computing itself be advantageous for the kinds of applications of machine learning that people are doing today? And that's a subtle question. One of the issues is that if you want to use a quantum computer for big data problems, there's a bottleneck just loading a lot of classical data into a quantum computer. It takes long enough to do that loading that can nullify the advantage of the quantum computer for some applications. So there's been a lot of interesting back and forth with people proposing applications of quantum computing. Then the classical team comes to bat and they say, actually, I can do that pretty well with a classical computer. That has been a very healthy back and forth. I think it has stimulated fresh thinking on the part of the classical team, and it's challenged the quantum team as we've explored the application space.
Yeah, I can certainly imagine a fruitful exchange and interchange there. So for the last part of this conversation, if you have a little more time you're willing to spend with us, I thought we would maybe turn back from the sort of the cutting edge of quantum computing to where some of these insights in quantum information have had an impact on the kinds of problems that you have studied, intermittently throughout your career, but certainly were perhaps a focus more early on, issues of information in black holes and the recent work that's taken place with ideas of holography and entanglement as relevant to the structure of space-time. Can we just walk through some of where you see the insights of quantum information sciences having an impact in such fundamental problems?
Yeah, to me, this is one of the most interesting parts of the story of quantum information and quantum computing, so that now people who are interested in understanding the quantum physics of space-time, and I think this also applies to the people who study quantum phases of matter, ideas about quantum computing are influencing the way people think about these things and giving them new tools for thinking about them. So you mentioned holography, which I'm sure you've talked about on previous programs. it's an amazing insight that it's possible to describe a system in which quantum gravity has a role, in which black holes are forming and evaporating and quantum fluctuations are occurring in space-time. We can describe that in an alternative language that doesn't involve gravity at all, which is more of a conventional quantum system. And but to understand how that works in detail, one needs to formulate the dictionary that allows you to translate a experiment or observation that you would make in the gravitational system into some feature of this so-called dual system that doesn't involve gravity. And it turns out that that dictionary is really, in the cases that we understand best, a kind of quantum error correcting code. And I think if the theory of quantum error correction had not been developed for the purpose of understanding how to prevent quantum computers from not functioning because of decoherence, that gave us new mathematical insights and tools which turned out to be applicable to the quantum physics of space-time. And similarly, in the case of quantum phases of matter, it turns out that some of the quantum materials that we study, both theoretically and in the lab, have sort of natural quantum error correction properties. They have this feature that the information stored in them is not locally accessible, like I described earlier. And so thinking about those systems from the point of view of quantum error correction has been very productive. Another thing is, in quantum computing, we think a lot about what happens to information as it's processed by a quantum computer. And what typically happens is you can load information locally, like put it on a single qubit, then you do a quantum computation, and it gets spread out among many qubits. Well, that happens in naturally occurring physical systems as well. We call it scrambling of information. And insights into how quantum computing describes that information scrambling have been applied to black hole physics. And we think that black holes are nature's most efficient information scramblers. So if you like, they're doing a quantum computation which scrambles up information faster than any other process that nature will allow. So these are examples of a few of the connections between quantum computing and other areas of physics. There are many more.
There's one fun example that I know you were pivotal, I guess you and Hayden, on this idea of the scrambling of information that's thrown into a black hole, a somewhat unexpected result in terms of being able to re-extract that information after it goes into a black hole. Can you just give us a sense of what that insight that you found shows us?
Well, what we considered, to put it in the form of a story, is someone, Alice, has this secret diary, and she doesn't want it to fall into the hands of her adversary, Bob, because there are a lot of embarrassing secrets in the diary. So, of course, she wants to destroy it. But Bob, in addition to being very curious, also has at his disposal very advanced technologies. So if Alice burned the diary, he'd be able to recover the information from it by examining the ashes and the smoke. And so burning it isn't a good idea. So what could be better than throwing it into a black hole, right, where it'll get completely torn to shreds, and Bob wouldn't dare enter the black hole, which would be very unsafe. But we know black holes emit Hawking radiation. So if you throw a diary into a black hole, we think eventually that information comes back out in the radiation, all scrambled up, but let's suppose Bob is so advanced that he knows how to unscramble it, he'd be able to read the diary. That's a very slow process. If it's a solar mass black hole, it takes 10 to the 68 years for the information to come back. So Alice feels pretty safe. But what Patrick Hayden and I noticed is that if that black hole has already been evaporating for a long time and Bob has been collecting the radiation as it comes out, if Alice throws her diary in, then Bob collects a few quanta coming out of the black hole in the Hawking radiation, and in about a millisecond he can read the diary instead of 10 to the 68 years. It's a lot faster. So this surprised people, and I think it, well, I should say, from the point of view of Patrick and me, it was a very kind of obvious consequence of things that people had been thinking about in the quantum information community, but it impressed the quantum gravity community. And I think it helped to accentuate the value of using quantum information concepts in the context of quantum gravity. So now somebody who wants to do research in quantum gravity typically learns a lot about quantum information.
Yeah, we had a conversation recently with Daniel Harlow, who was describing, you made reference to it, how quantum error correction is vital to the dictionary in the holographic principle between the way information is encoded on the boundary of a region and the way information is encoded in the interior, in the so-called bulk of the description. And I gather, we discussed this a bit with Daniel in that conversation, but without the architecture of quantum error correction having been developed for these other purposes, I don't know that we would have the result as he articulated. I mean, is that an example of where there's this fruitful and unexpected interchange between quantum computation on the one hand and gravitational physics on the other?
Yeah, it's an interesting question. How long would it have taken to figure it out if we didn't already know about quantum error correction for other reasons? I don't know.
Yeah. But it's a beautiful application of the ideas from one subject into one that's completely different. While it's a little bit slightly off topic, it's just sort of a fun thing, talking stories. You mentioned this idea of Hawking radiation being vital to the story you were telling about Alice and her diary, and Bob being able to reconstruct it in the manner that you described. You famously, at least in the field of physics, had a bet with Stephen Hawking regarding information coming out or not coming out of a black hole. Maybe it's just sort of a fun thing to end on here. What was that bet and how did it resolve?
Yeah, even among non-physicists, I was famous for about 24 hours. Well, so Stephen and I had some history going back a ways. I first met him at a conference in 1982. And, he had a great sense of humor. And I discovered, and I'm not sure what made me so bold, that he liked it when, I would make snide, sarcastic remarks. He would make some, you knew Stephen, he would sometimes make statements that seemed to come out of the blue and it wasn't clear what they were based on. So I would say things like, well, what makes you so sure about that, Mr. Know-it-all, And he actually appreciated this, which was nice, so I kept doing it. Anyway, so we would have conversations in which we would argue in kind of a good-natured way. There were actually 3 bets we wound up making. But the most famous one that you're referring to was about what happens when information falls into a black hole and evaporates completely. And this is really, although the bet was just for fun, the issue itself is a deep one that a lot of physicists are concerned about and think about, because it's a collision between 2 fundamental beliefs. On the one hand, we referred to it earlier, causality. Information can't travel faster than light. That seems to say that once something falls into a black hole, it'll never get out again. But there's also a principle, which we sort of referred to as well when we were talking about the Everett interpretation, that nothing happens in the world except unitary evolution. In other words, information is never destroyed or created. It just gets scrambled up into forms that are hard to recognize. So the causality point of view seemed to say, and Stephen had been arguing this for years, that information that falls into a black hole is destroyed completely and can never be recovered in the universe. And the quantum mechanical point of view, that information can't be destroyed, would say that when the black hole finally evaporates, the information is present, albeit in a very scrambled form. So that's what the bet was about, whether information is destroyed or not. And Kip Thorne was also involved. He was siding with Stephen, actually. And it was in 2004, and it was quite a surprise to me after we'd been arguing about this for quite a while. Stephen decided to concede this bet. And he did this in a very public way at a conference that was in Dublin. And Kip and I were at that conference for other reasons. We were giving talks about other topics. Stephen made a request kind of at the last minute to be added to the conference program because he wanted to announce something. And he announced that he had changed his mind, that he now believed information does survive, does come out of black holes when they evaporate. And he presented to me, to settle the bet on that occasion, a baseball encyclopedia, because the terms of the bet, since it was about information, said that the loser was to present the winner with an encyclopedia from which information could be acquired at will. And he knew I liked baseball. Now, it's not easy to get a baseball encyclopedia in Ireland.
Yeah.
So he had to have it ordered. It arrived, overnight shipment, just in time, so that he could present it to me. And not knowing what else to do, I, took the encyclopedia and held it over my head like I just won the Wimbledon championship or something. And those pictures were widely disseminated in the media, like in Time magazine and so on. Now, I had mixed feelings about this because I didn't really think, and it was a little disappointing in a way, that after all, the years of arguing, that we couldn't do that anymore because Stephen had changed his mind. And his grounds for changing his mind were, in my view and that of other physicists, not very convincing. He was kind of on the right track. He had a particular way of doing the computation to show that the information comes out. Well, I don't know, I don't want to get technical, but it was what we call a semi-classical computation. And I didn't think it was likely to be the whole story because, I thought in order to understand how the information comes out, we have to understand all the microscopic degrees of freedom of the black hole and what that entropy means and so on. And that computation seemed to, circumvent all of that. Then 15 years later, people doing a very similar but far more convincing computation, which was also semi-classical, got the same kind of answer that seemed to show the information was coming out. And that.
But would you say that fundamentally it was Maldasena's discovery, ADS-CFT, which could be translated into a black hole in the interior of a region being described by an ordinary non-gravitational quantum system on the boundary, where it's like information just has no place to go in that description? Was that fundamentally underlying his change of heart?
From my point of view, it was. Stephen never put it that way. However,
Right.
I think he was profoundly impressed by Maldasena's discovery of holographic duality. And one could take the point of view, which was not exactly Stephen's point of view at the time, that at least in the context where Maldasena's observation applied, which, by the way, is not the real world, it's a kind of
Right.
toy model that differs
Sure.
from our world in some important ways, like the dark energy is negative instead of being
Yep.
positive and so on. But within that setting, once you saw that there was a dual description, which was precise, which didn't involve gravity at all, then it kind of settled the matter that the information doesn't get destroyed, because we can describe everything in terms of the Schrodinger equation. But to be honest, I'm not completely satisfied. I mean, I think that what I just said is correct as far as black holes and anti-de Sitter space is concerned, but we'd like to understand the mechanism by which information is getting out, I think, in greater detail than we currently do. And we'd like to understand how to think about the inside of black holes, including the singularity, where we're still pretty clueless.
And where do you think, again, maybe sort of a final quick discussion of that. So, I think we've made a lot of progress, as you've made reference to, in understanding black holes as viewed, perhaps you can say, from the external observer's perspective, the Hawking radiation that comes out, issues of information storage on the event horizon and so forth. Where do you think we stand on fully articulating the interior of a black hole, including the singularity?
I don't think we know much about it. I think we know there's a story about how part of the interior is encoded on the boundary in the case of ADS-CFT, but we don't really understand how to describe everything that's going on in the interior in that language. But there's another point that I'd like to make, which is it's not the world that we really want to understand, right? We want to understand the universe, which has positive dark energy. We'd like to understand cosmology. We'd like to understand not just black holes. We'd like to understand what does quantum gravity have to say about the very early history of the universe. Because even if you don't live in a black hole or near one, everybody lives in the universe. So we all care about that. And there are some insights that we have had from thinking about black holes that have influenced our point of view of cosmology, most notably because black holes emit Hawking radiation, which is a quantum effect. That led to the realization that there should be quantum radiation present also in the early universe when it was very rapidly expanding. And those fluctuations would give rise to variations in the energy density of the universe, and those would grow from gravitational instabilities, and the dark matter would fall into them. And this would give rise to seeds for galaxy formation and clusters of galaxies. That's the best idea we have about where the structure of the universe came from. And it really began with the insight of Hawking radiation, I would say. And it's been partially validated by observations of the cosmic microwave background, though.
Yeah,
We
very
would like
much
to
so.
know more.
Yeah, a huge cosmological success story. Final moment here. Are you still a baseball fan? You mentioned Hawking giving you the baseball encyclopedia in Ireland. Is that still a passion?
You know, I mean, I still love baseball, but I just don't follow it as closely as I once did. There are too many other distractions.
Yeah.
But it was part of my formative years. You know, I first got interested in statistics from looking at the back of my baseball cards when I was about 6 years old. And it really made a big impression on me that you could encode the performance of a player in those numbers. And, you know, that's an example of how we try to use mathematics to characterize how the world works.
There you go. Probabilities at the early age of looking at Topps baseball cards. But you must have a sense. I mean, Shohei Ohtani, best baseball player. Do you have a view on that?
Well, yes. I wish he would stop pitching, though. I mean, he's a great pitcher, but I think if he just concentrated on hitting, he would have he'd be of more value.
Well, I
And
guess
I'm
that's yeah, go ahead. I mean, that's what Babe Ruth did, I guess, right? He started
That's
pitching
right.
and hitting the, yeah.
Of course, Babe Ruth was also a great pitcher.
Yeah.
And well, I'm more up on, you know, when Ohtani really broke through and became a star, I was a little bit skeptical because his on-base percentages weren't that great. You know, he wasn't that patient a hitter, and but he's improved a lot in that respect. So
Yes,
now
he's
he's got
definitely,
yeah. All right, but
Definitely settled in.
Incidentally, Aaron Judge is also great. So
Yeah, I was going to ask you Aaron versus Shohei, but that's a complex bi-coastal issue, so perhaps we'll leave that more difficult question to another day. So John, I just want to quickly mention, I noted that we had a conversation not long ago with Daniel Harlow, and some in our audience may have seen that or would enjoy seeing that too. At the end of that conversation, Daniel reminded me that he was my student in a course that I taught at Columbia on geometrical methods in physics. So I can't help but saying that, you know, I was a student of yours at Harvard back in the 1980s, where you taught a beautiful course on classical physics. So we sort of see the lineage of, you know, teacher to student and then teacher to student again. And it's just sort of a wonderful way in which science progresses, you know, generation upon generation.
Well, let me say something about that, because knowing we were going to have this conversation, I checked my records.
Yeah.
And it was the fall term of 1982. You took my classical mechanics class, and you got an A.
Yeah, there you go.
And I'm glad I got that right.
God, thankfully. Boy, what if I didn't do well? We would have to cut out this part of the
I worked very hard
conversation.
on that course, by the way.
Well, you did an amazing job, and I have to tell you, I don't know, you probably remember, but at the very end, the final topics that you did was classical field theory. You know, for the most of the course we were doing, you know, TOPS processing and the things that you typically see in a course. But that final section on classical field theory, that was the one that captured me. And that propelled me forward. I mean, once I got a taste of field theory, even in that classical setting, you know, this is the subject that I had to study. So that was really amazing and quite impactful.
Well, it's very kind of you to mention that.
Absolutely. So, and thank you. It's very kind of you to spend the time here this afternoon in this exciting arena of quantum information science, quantum computing, you know, spanning, of course, the fundamentals of quantum physics to the technological applications of these ideas, and finally, you know, the stuff that we spoke about at the end on applying these ideas to fundamental problems in black hole physics and space and time and gravity. It's just a hugely exciting area. So I just wish you the best going forward, and thanks for spending the time.
Well, this has been a lot of fun. Good to see you, Brian.
Thank you very much. See you soon. Bye.
Bye-bye.